We are on AP Review, FRQ Topic 3, Data Questions. These are questions that involve a table of values for some function. And they can ask many different types of questions, some of which are these. They oftentimes will ask you to approximate a derivative of that function. And remember that a derivative of a function, the approximation for the derivative, is just delta y over delta x. This will be at a certain value of x or t or whatever your independent variable is. And so you want to choose values for x that are immediately surrounding the value that they give you here. You might also be asked to approximate an integral. Okay, so remember that an integral, to approximate an integral, we have several ways to do that. We can use a left Riemann sum, a right Riemann sum, we can use a midpoint sum, and a trapezoidal sum. So those are all, and they would tell you which of those to use in your approximation. They might ask you to state the meaning of a derivative. They usually combine the meaning with your approximating the derivative. They'll say approximate it and then state the meaning of it. Sometimes they pose it like that. And you want to give this meaning in the context of the problem. Also meaning of an integral. Okay? They might ask you that. You need to know for these the average value of a function. So let's review briefly the average value of a function. We used the notation f, AVE, and they will give you boundaries for this. And the equation for that is 1 over b minus a times the integral a to b of your function. Okay, remember, if you're finding the average, your average tests, you add up your test scores and then divide by the number of tests. That's how we remember that. So average value of a function. F here, F there. You're finding the average of F. Okay? Another thing that you might need to know is the intermediate value theorem. Intermediate value theorem. For the intermediate value theorem, the function has to be continuous. So f has to be continuous on the closed interval that you're dealing with. And that's the only requirement to use the intermediate value theorem. And what the intermediate value theorem says is if you have some value, I'm going to call it C, if C is between f of a and f of b, so keep in mind these are the y values, these are the y values. So there's some other y value that's between two y values. And of course it's between, so this number, this value could be less than the other one. So just between. If this y value is between the other two y values, then by IVT, but you don't have to say by IVT, you can just say then there exists some x value such that, and this x value will be between a and b, such that f of x is equal to that C value. All right, so the intermediate value theorem says there has to exist this X value that makes F equals C. Okay? They also might ask you a mean value theorem question, MVT, mean value theorem. And let's go over that quickly. For the mean value theorem, F has to be continuous on the closed interval, so that's the same as that one for the IVT. But there's an additional requirement for MVT. F has to be differentiable on the open interval. So it doesn't have to be differentiable right at A and B, but it has to be differentiable everywhere in between there. The way I think of MVT, remember, the way I think of MVT is you have like A and B. Here's your X is equal to A, X is equal to B. That slope is, there's some other X value at which the slope is the same as the slope from A to B. So this slope, that's that slope, is equal to this slope. And so that value, that X value there would be X is equal to C, okay? So continuous and differentiable. And then if we find that average slope, so I think I'm going to write that as f of b, that average slope would be f of b minus f of a, so the difference of the y's over the difference of the x's is equal to some number, I'm going to call it k. Then we can say that by MVT, but we don't have to say by MVT, we can just write therefore, so therefore there must exist some C in A to B, actually not including the boundaries A and B. It must be inside A to B such that F at C is equal to that slope that we found. Okay? So F of C is equal to this slope. Alrighty? Alright, let's go look at some problems. I'm going to start with the problem from 2018. So pull out your problem from 2018 here. It's the first one on your list, on your worksheet. This one is a no calculator problem, and most of these are no calculator problems. There's really not a way to use a calculator on most of these. So it's fine that we don't have one because we couldn't do it anyway. All right. In 2018, there was this problem. The height of a tree at time t is given by a twice differentiable function. Twice differentiable function, there's probably a reason they're giving us that, okay? That's a very specific thing to tell us, right? So we'll probably have to use that sometime. H, where h of t is measured in meters and t is measured in years. Selected values of h of t are given in the table. So here are selected values of h of t, but we know that h is twice differentiable, so we know that h is continuous and once differentiable. Part A, use the data in the table to estimate h prime of 6, and then using correct units, interpret the meaning of h prime of 6. Okay, so h prime of 6 is approximately equal to, all right, so I'm thinking, in my head I'm thinking delta h over delta t, around x is equal to 6. Change in h over change in t, because that's what a derivative is, right? So I go over here, t is equal to 6 would be right here, so I'm going to be using the 5 and the 7 for t. So I could write this as delta h over delta t from t is equal to 5 to 7. Okay, that would be a one way to write it. And then I can say, well, that is h of 7 minus h of 5 divided by 7 minus 5. We could also switch the 5 and the 7 on top and bottom and get the correct answer that way as well, to give us the same thing. H of 7 is 11, h of 5 is 6, and there is my safe stop answer, right there. So that is my approximation of h prime of 6, and now we're going to interpret the meaning. Okay, so h is the height of the tree, t is in years, so h prime, if we look at we have meters over years, right? So the units for h prime are meters per year. That's a growth rate, right? H prime of 6 is the rate the tree is growing in meters per year. You can write out meters per year in words if you want, or you can do meters divided by years, either way. So h prime is the rate the tree is growing in meters per year at time t equals 6 years. Okay, important. You need to say on any of these interpret ones, you need to say what it is. So this is the rate of growth. It's the growth rate. You need to say what it is. Then they expect two sets of units. They want units for h prime and they want units for the time. Every time they want both of those. So make sure it's units. Make sure you don't just give the units for h prime. People tend to forget this one, so make sure you give the time units as well. Okay, part B. Explain why there must be at least one time in between 2 and 10 such that h prime is 2. Okay. This is an MVT problem. I know it's MVT because they're asking, we're given the h and they're asking me to state why there must be some special value of h prime. So I know it's MVT. Okay, so I'm thinking to myself, the first thing I'm going to do is give my conditions for MVT. You don't have to say this first, you could say it second, but it needs to be said before we give our statement that therefore there must exist a time, blah, blah, blah. Okay, so I'm going to start with that. I'm going to say, all right, h is given to be twice differentiable. That means h is twice differentiable, not just from 2 to 10, but everywhere, right? So it's given to be twice differentiable. Therefore, h must be both continuous and differentiable. Not only from 2 to 10, but for everywhere. So I'm just going to stop right there and say that. All right, I don't need to state from 2 to 10 because it's continuous and differentiable everywhere. So of course it is for 2 to 10. All right, now I need to go. Those are the conditions. So now I need to go and find out where is the slope equal to 2. Okay, so where is h prime going to be equal to 2? So I come up here, remember that h prime, remember that's delta h over delta t, right? So we want to find a spot where this is equal to 2. We want to find 2 times for which that is 2. So I'm looking at, like, they gave me 2 to 10, so I always will start at 2 to 10. I'll start with what they give me, and hopefully that's it. But if not, we need to go inside there. Delta H is 13.5. Delta t is 8. And 13.5 divided by 8 is not 2. So I cannot use 2 and 10 for my 2 times. I need to go find 2 other times. So I'm looking around, I'm looking at other things. I don't think I'm going to be using that 1.5, so I can rule out that 2. Come around here. This difference is 9. This difference is 4. Well, 9 over 4 is not 2. This difference is 4, and that difference is 2. And 4 over 2 is 2. So I've found my 2 times. I've found my 2 times, 3 and 5, for which delta h over delta t will be 2. So that's what I'm going to use. I'm going to say h of 5 minus h of 3 over 6 minus 2 is equal, over 5 minus 3 is equal to 6 minus 2 over 2, and that is 2. I need to say that because those need to match, right? So now I can say therefore, you can use 3 little dots or the little arrow here, therefore there must exist. And you can come up here, you guys, and write this exact thing. You can come and rewrite that exact thing. Therefore, there must be at least 1 time t for t between, and you can say 3 to 5 there, such that h prime is equal to 2. I'm going to write it using my little symbol. So there exists some t in 3 to 5 such that h prime of t is equal to 2. Condition, and then there's the meat of the problem, delta h over delta t is equal to 2, and then your statement, right? Okay, part C. Use a trapezoidal sum with 4 subintervals to approximate the average height of the tree. The average height of the tree. Well, alone the trapezoidal sum would only approximate the integral. We don't just want the integral here, we want the average height of the tree. So they're asking us not just for a trapezoidal sum using this data, they're asking us for the average height of the tree. Well, the average height from 2 to 10 will be 1 over 10 minus 2 integral 2 to 10 of h, right? So the trapezoidal sum will approximate this part, but we need to make sure we keep this part. So now I'm going to say it's approximately equal to 1/8. And now here comes my trapezoidal sum. So trapezoidal sum. The formula, remember the area of a trapezoid, don't write this down on your AP test, but the area of a trapezoid is 1/2 the base, actually it's 1/2 the height times the sum of the bases. So when we're doing it, we don't forget that 1/2. It's like 1/2 base times height for a triangle, except there's going to be two y values here. So the base is going to be our t difference. So we start at 2. So the first base here is going to be 1. And then we multiply by the sum of the two y values, right? The heights. So 1.5 plus 2. That takes care of the first trapezoid. The next trapezoid, 1/2. Now I go to the next piece, the 3 to 5. Well, that base is going to be 2. And then I'm adding 2 plus 6. That takes care of the second trapezoid. Third trapezoid, 5 to 7 is 2. 6 plus 11. And then our last trapezoid, base will be 3. And the height is 11 plus 15. And I'm going to close that bracket and stop. That is the trapezoidal sum. That's the trapezoidal sum, and by multiplying by an eighth, we get the average height. Okay? All right. Part D. The height of a tree in meters can also be modeled by, so not only can it be modeled, not only does it meet these, but it can be modeled by this function g. Can be modeled by that function g, where x is not time, x is the diameter of the base of the tree. So x is the diameter of the base of the tree, not time. When the tree is 50 meters tall, the diameter of the base of the tree is increasing at a rate of 0.03 meters per year. So they are saying the base of the tree, which is x, that's x, x is increasing at a rate of 0.03 meters per year. So they are giving me dx dt there. Dx dt, because it's a rate, right? Dx dt is 0.03 meters per year. Okay? According to this model, what is the rate of change of the height of the tree? So we're supposed to find the rate of change of the height of the tree. So they're asking us for dg, because g is the height here. What is dg dt when, at the time when the tree is 50 meters tall? 50 is not x. 50 is your g value, right? At the time when g is 50 meters tall. So that's what we're looking for. I have the equation for g, I have dx dt, and I'm looking for dg dt. So this is a little related rates problem. They give me g is equal to 100x over 1 plus x. For a related rates problem, we're going to come in, we're going to take the derivative of both sides with respect to t. Okay? On the left-hand side, I will have dg dt. On the right-hand side, I'm going to use the quotient rule, but remember that we're taking the derivative with respect to t. So anytime we take a derivative of an x expression, we need to multiply by dx dt. It's implicit differentiation. So we start at the top. The derivative of 100x is 100 dx dt. Then we multiply by the bottom. Minus, now we're going to now we need the derivative of the bottom. So that is 1 dx dt, or just dx dt, times the top, all divided by the bottom squared. So that is dg dt, and now we're going to say, okay, so at g equals 50, I need to evaluate this when g is 50. Well, there are no g's, but there are some x's, right? So I need to come off to the side and find out what is x when g is 50. I'm going to take my g equation, put in 50 for g, and solve that for x. So I have 50 plus 50x is equal to 100x when I multiply both sides by 1 plus x. Subtract 50x from both sides, and we find out that x is 1. So at g equals 50 and x equals 1, I'm going to plug in x equals 1 for all my x's, and I'm going to plug in 0.03 for my dx dt. So right there, my dg dt will equal 100 times 0.03 times 2 minus 0.03 times 1 times 100 is 100, all divided by 2 squared. And I would just say stop right there. Let's take a look at how they scored this. Let's take a look at how they scored this. For part A, they gave 1 point for that estimate and 1 point for the interpretation with units. So again, both sets of those units. I know I've stressed that. It's because I see kids forget that. Okay, for part B, they gave 1 point for h of 5 minus h of 3 over 5 minus 3. They gave 1 point for that. And then they gave 1 point for the conclusion using the mean value theorem. Okay, and again, you don't have to say by mean value theorem. You have given everything for the mean value theorem and then made your conclusion after that. For part C, they gave 1 point for the trapezoidal sum and 1 point for your approximation. So 1 point just for the trapezoidal sum and 1 point for the 1/8 of that value. And in part D, they gave 2 points for the derivative of g of x, or just of g. So that's this part right here. Okay? And then 1 point for your answer. Little side note for the scoring on this one, they gave a maximum of 1 out of 3 if we did not use the chain rule, that implicit differentiation, if no chain rule used. So if we didn't do the dx dt here, at most we would have gotten 1 out of the 3 points. Okay? All right, next up I'd like to do the problem from 2016. So let's take a look at that, 2016. Again, there's a table with values in it. So let's take a look at this one. Water is being pumped into a tank at a rate. Oh, this sounds like a rate-in problem, doesn't it? It is. It's a rate-in problem. Water is being pumped into a tank at a rate modeled by this, W. That is our rate in. Okay? 0 to 8. All right. Let's see. That's liters per hour. T is in hours. Water is removed from the tank, so rate out at a rate modeled by R. So that, and some values are given in this table, right? So that is our rate out. It says that R is differentiable and decreasing. Okay, there's probably a reason they gave us that. So we'll have to keep that in mind. Selected values of R are shown in the table. At time 0, there are 50,000 liters of water in the tank. They gave us an initial condition there. So the amount, if I let A be the amount later, the amount at 0 is 50,000 liters. Okay? All right. Part A. Estimate R prime of 2. Okay, R prime of 2. Estimate. So I come up to the table, I find the time values that are closest to 2. Do not use 0 and 8. Use the 2 that are closest to 2. And I will say that R prime of 2 is approximately equal to delta R over delta T from time 1 to 3. And that will be R of 3 minus R of 1 over 3 minus 1. And r of 3 is 950. R of 1 is 1190. And 3 minus 1 is 2, or you can just write 3 minus 1 and say stop right there. Okay? It says to indicate units of measure, so I need to give units for this. R's units is liters per hour. The time units are in hours. So this will be liters per hour per hour. Top over bottom, liters per hour per hour. And you can write it like that if you want to. You can write liters per hour, and you can write it out in words, and that's fine. Or you can write it liters per hour squared. That will work as well. Okay? Either way. All right, part B. Use a left Riemann sum with 4 subintervals indicated by the table to estimate the total amount of water removed during 8 hours. Well, the total amount of water removed is just the integral of r from 0 to 8. So the total amount removed will be the integral from 0 to 8 of r of t. And we can approximate that with just a left Riemann sum. So let's come up and do a left Riemann sum. For a right or left Riemann sum, remember we're just doing rectangles. So base times height. And we're going to use the leftmost height of each base. So the base is 1. The first height for a left Riemann sum will be 1340. So 1 times 1340. Plus, the next base is 2, and the next height is 1190. 2 times 1190. The next base is 3, and the next height is 950. And the last base will be 2, and the last height will be 740. In a left Riemann sum, you do not use the rightmost y value. In a right Riemann sum, you do not use the leftmost y value. Don't know if you guys remember the little Kit Kat activity that we ate, that we did not use. We had to eat off one of the sides because we were not going to use that in the right or left Riemann sum. Okay, and I can just stop there. Make sure on these, and I should have mentioned that with that trapezoidal sum, make sure that you do write all of the values. Back here on this trapezoidal sum, make sure that you do write the 1 there. Make sure you do not add these numbers as you put them down. Write every number out because we need to see where those came from, not just totaling up an answer, okay? So write all of these values each time, okay? So write the 1 there, okay? And then we need to say, okay, is this an overestimate or an underestimate of the actual total amount of water removed? So we come up here to our information. They told us that R is decreasing. R is decreasing. So R here is decreasing. And we used a left Riemann sum. So we used values each time that will make these rectangle areas larger than the area under the curve. So since we used a left Riemann sum on a decreasing function, we will get an overestimate. And that's exactly what we're going to write. Since we used a left Riemann sum on a decreasing function, we have an overestimate of the actual amount. And that's all we need to say. Three main things. Left Riemann sum, decreasing function, overestimate. Three main things they're going to be looking for there. Okay. All right, part C. Use your answer from part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. Okay. So this goes back to what we did on the last topic with our rate in, rate out problems. We want the total amount of water at the end of 8 hours. We have the total amount of water that we start with, and we want the amount at 8 hours. So we are going to set up a fundamental theorem of calculus. But first I need to tell them what my A is. So I'm going to say let A of t be the amount of water in the tank at time t. So A will be in liters, right? So I can say that A of 8, that's the amount at the end of 8 hours, minus A at 0 must equal the integral from 0 to 8 of A prime. Fundamental theorem. But A prime is my rate in minus rate out. So I'm going to write that. So this will be my rate in, which is W of t, minus my rate out, which is R of t, dt. Okay, A of 0, what we start with is 50,000. And I have two functions. I'm taking the integral of a difference of functions, so it's the integral of this minus the integral of that, right? So this will be the integral from 0 to 8 of W of t minus the integral from 0 to 8 of R of t. Okay? So A of 8 will equal, I'm going to take this 50,000 to the other side, plus, okay, I didn't even mention this, but this is a calculator problem. This is a calculator problem. It was number 1. That's with a calculator. Should have mentioned that up there. But that's with a calculator. So that's how we're going to evaluate that integral right there. So with my calculator, I'm going to say math 9, 0 to 8, of W of t, let me type that in here, 2,000 e to the negative t squared over 20, negative x squared over 20, with respect to x. So we get 7,836. I'm going to round that to the nearest 3 decimal places, since everything else is going to be, I'll probably give it a couple extra decimal places. It never hurts. We only have to do 3 here, but oops. 7836.195325. Why not? Just give everything that's on my screen here. And then plus, and now, I'm sorry, not plus, minus. Now I need our approximation. This is an approximation, so I'm going to come up here and change my equal sign to an approximately equal sign, because this left Riemann sum that approximated this integral was just an approximation, right? So minus, now we have a choice. We can type all this into our calculator, or you can just write all that out again. And I think I will just write all that out again. 1340 plus 2 times 1190 plus 3 times 950 plus 2 times 740. Close that parentheses because I'm subtracting that whole thing, and I'm done with that problem. Okay? If you add all that up, you get 49786 if you add all that up. Now, oh, you know what? I've just reread this, and it says to the nearest liter. So I thought I was being so clever writing all that out, but we need to make this to the nearest liter, so I'm going to have to go in and add it all up. When I add it all up in my calculator, I'm not going to take time to type all that in, but when I do add all that up to the nearest liter, I get that. So it's this to the nearest liter. All right. I should have read that first, and that way I would not have written that, but that's okay. That's okay. Part D. For 0 to 8, is there a time when the rate at which the water is pumped into the tank is the same as the rate at which water is removed from the tank? So rate in, is there a time when rate in equals rate out? Well, rate in for us is W of t. Rate out is R of t. And we're asked, can that happen? And if so, well, just can that happen? Is there a time when that happens between 0 and 8? And I will tell you that the first time I saw this problem, this one made me think for a while. I don't know that I would have been able to finish this in the time that they gave me. But this one made me think a little bit, because I looked at the function, and I looked at these R values here, and I was trying to come to terms with it, and it took me a little while to figure this out. But I thought of a way, if these are equal, if so, then W minus R would have to be 0, right? If they were equal, then their difference would have to be a 0. So I thought, okay, let's just see, and this was really what I did. I thought, okay, let's see what this is at time 0. At time 0, let's see what that is, and let's see what it is at time 8. So I thought, okay, at time 0, W of 0 minus R of 0 would be, okay, so then I came to my calculator, and at this point, since I was going to be doing a couple of these, I went ahead and typed W of t in for y1, so 2000 e to the negative t squared over 20. And then I just did y1 at 0. So y1 of 0 is 2000. R of 0 is up in my table. R of 0 is 1340. And so I got 660 for that. And then I said, okay, what about W of 8 minus R of 8? So W of 8 is 81.524, and R of 8 is 700. And as soon as I saw that, I thought, ooh, I'm on the right track, because I'm going to get a negative number here, right? So I'm going to take that and subtract 700, negative 618. Okay? So, At time 0, this difference is a positive number. At time 8, this difference is a negative number. This function is always continuous, and they gave me that r of t is differentiable, therefore r of t must be continuous. I have two continuous functions, so their difference is also continuous. Therefore, the intermediate value theorem must hold true. And there must be a time when the difference is 0. Now it's just a matter of saying all of that. So w of t is continuous, and r of t is given to be differentiable, and is therefore continuous. Okay, so w of t minus r of t is continuous. And now 0 is between I guess since this was lower, I'm going to write that first. W of 8 minus r of 8 and w of 0 minus r of 0. 0 is between those two. Therefore, the IVT, intermediate value theorem, holds true. So therefore, there must be a time in 0 to 8 such that w of t equals r of t. It's kind of a long one, kind of a stinker of one. Part D often is. Let's see how they scored this. 1 point for the estimate, 1 point for the units in Part A. 2 points. Okay. Part B, that was worth 3 points. 1 point for your left Riemann sum. 1 point for the estimate. 1 point for stating it's an overestimate with reason. So this left Riemann sum is this. That's the left Riemann sum. And the estimate is also that, since I didn't evaluate this. I didn't, like if I had added this up and got a value, that would have been the estimate. But if I don't, then this is my safe stop estimate. So this counts for both of those points. And then the overestimate with reason. Okay, part C was worth 2 points. 1 point for the integral, 1 point for the answer. So 1 point for that integral, and then 1 point for the answer. And then part D was worth 2 points. 1 point for considers w of t minus r of t. You consider that. And then 1 point for your answer with explanation. Okay? Next up, we're going to take a look at 2014. Okay. For 2014, we have, it says train A runs back and forth on an east-west section of railroad track. So train A is going east to west, and since they have a train A, I'm kind of thinking later on in this problem we might find some information about another train B, right? So, but train A runs east to west. train A's velocity, measured in meters per minute, is given by a differentiable function. It's differentiable. It's probably a reason for that. Function v sub a of t, where t is measured in minutes. Okay. Selected values are given in the table. Okay. Part A, find the average acceleration of train A from 2 to 8. Average acceleration. Well, the average acceleration will be acceleration, right? This is my thought process. It will be acceleration. It's the average acceleration. So to get acceleration, I need the derivative of velocity, right? So I need, this is going to be delta v over delta t, right? From t equals 2 to 8. That's the average acceleration. So delta v will be v at 8 minus v at 2, and delta t will be 8 minus 2. So v at 8 is negative 120, v at 2 is 100, and 8 minus 2 is 6, or you can just keep it 8 minus 2 and not risk it. Okay, so this is the average acceleration. I'm looking, did they ask me for units? No, they didn't ask me for units. So I'm done with that part. Okay, part B. Do the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some time t? Okay, from 5 to 8, with t between 5 and 8. That's really specific. So from 5 to 8, is there some time where the velocity has to be negative 100? So let's go look. From 5 to 8, here are your velocities. Must there be a time where the velocity is negative 100? Yes, if v is continuous, because then we would use the intermediate value theorem. So is v continuous? Well, did they tell me that v is continuous? They told me that v is differentiable, therefore v must be continuous. Therefore, yes, there must be a time, by intermediate value theorem, there must be a time where v is negative 100. So now it's just a matter of writing all that out. Okay. V sub a is given to be differentiable. Therefore, v sub a is continuous. Right? And now I need to state that negative 100 is between these two values of v at those times. So v sub a of 5 is 40. V sub a at 8 is negative 120. Therefore, negative 100 is between v sub a of 8 and v sub a of 5. Okay? So, there exists sometime t with t between 5 and 8 such that v sub a of t is equal to negative 100. And again, you can totally write these out with words. You do not need to use these little symbols. I just do it to save time, but you can totally write it out in words. All right, part C. At time 2, train A's position is 300 meters east of origin station. So if we have the origin station at the origin, train A's position is 300 meters east of there. So it's 300 meters east, and it's heading east. So it's 300 meters and it's still moving east, right? Write an expression involving an integral that it gives the position of train A in meters from the origin at time 12. So they gave me an initial condition and they asked me to find another position. So yeah, we can do that. I think I'm going to let x, since train A is moving east to west, it's moving on the x-axis, so I'm going to let x of t be the position of train A at time t. So then I can say x at 12 minus x at 2 is equal to the integral from 2 to 12 of x prime dt. But x prime is our velocity function, right? So x prime is v sub a of t. So I will say that x of 12 minus 300 is equal to the integral from 2 to 12 of v sub a, of t. I was looking at the problem. Now we're supposed to use a trapezoidal sum with 3 subintervals to approximate that integral. Okay? So x of 12 is approximately equal to, I'm pulling that 300 to the other side, and now I'm going to add the trapezoidal sum from 2 to 12. Be careful with that. We only want it from 2 to 12, not from 0 to 12, only from 2 to 12. So I'm going to ignore this piece here. Trapezoid. So 1/2 the base times the sum of the heights here, right? So 1/2, the first base is 3, and the two heights are 140. Write it all out. Don't actually add 100 plus 40 there. The next trapezoid will be base is 3, heights are 40 and negative 120. So 3 times 40 plus a negative 120. And then one more. Then last base is 4, and the heights are negative 120 and negative 150. So 4, negative 120, negative 150. I'm going to close my bracket here, get it all in here, like that. Okay. And that is the approximation for the train's distance at time 12. And I'm not gonna figure it out. I'm not gonna add that together. I'm just gonna leave it right like that. Okay. Part D. A second train, B, travels north from origin station at time t. The velocity of train B is given by v sub b of t. Sorry, v sub b of t. Wow, that's a tongue twister for me. Okay, so they're giving me a function for the velocity of b. And at time 2, the train is 400 meters north of the station. So I'm going to draw this again. So it's still at time 2, and we were given A's position at time 2, right? So at time 2, A is right here, and B is up here going north, right? It's going north. Find the rate in meters per minute at which the distance between train A and B is changing. So rate find the rate at which the distance is changing. So there's the distance. I think I'll call that distance C because I see a little triangle there. You can call it anything you want, but I think I'm going to call it C here. So I know an equation. If I let this distance be x and this distance be y, then I know an equation that relates those three. It's called the Pythagorean Theorem. So I said let x equals the position of train A. I need to do the same. Let y equal the position of train B. At time t, and let C be the distance between train A and B at time t. Then C squared is equal to x squared plus y squared, and I want the rate of C. So I want dC dt, right? So I'm going to take this, it's a related rates problem, take the derivative of both sides with respect to t. So this will be 2c dC dt is equal to 2x dx dt plus 2y dy dt. I can divide both sides by 2 and the 2's will be gone, right? So now I need to find some values. So x, I'll use the same pen. X at 2 is 300. Y at 2 is 400. So C at 2 has to be 300 squared, the square root of 300 squared plus 400 squared, right? The square root of 300 squared plus 400 squared. That's all at time 2. Okay? Now, dx dt is, in fact, I'm going to write that down. dx dt is the velocity of train A at t. Oops, y. dy dt is the velocity of train B at t. Okay, so now I can put these values in for x, y, and c. So I'll say at time t equals 2. All right. I'm looking for dC dt, so I guess I'll write that out. So I have the square root of 300 squared plus 400 squared, which will be 500 if you use our little 3, 4, 5 right triangle, but I can always just write it like that too, so that's fine. dC dt is equal to x is 300, V sub a at time 2 is in the table. It's 100. So V sub a at time 2 is 100. Y at time 2 is my 400. And now I need the velocity of B at time 2. So let's come up here and find that. The velocity of B at time 2 will be, I'm putting just 2 in for t here. So negative 5 times 4 plus 60 times 2 plus 25. And I'm going to figure this out, but you could also just write that out right there if you wanted to. Negative 20 plus 25, that's a 5. So this will be 125. And so dC dt is equal to 300 times 100 plus 400 times 125 divided by that square root. And again, that square root is 500, or you could just write that square root again, and that's fine as well. Do I need to give you, I'm looking up here, do I need to give units? They don't ask me for units, so it's safe for me not to give units here. But the units, well, they gave you the units, meters per minute, so there we go. We didn't have to repeat that. Let's look at how this was scored. We have in part A, that average acceleration, that was just worth 1 point for the average acceleration. Okay, part B was worth 2 points. 1 point for stating that the that negative 100 was between the two velocities at time 8 and time 5. And then 1 point for your conclusion using IVT. Again, you don't have to say by IVT, you just have to use all of the, it has to be stated, you are using it, you're just not saying by IVT. So 2 points for that. For part C, it was worth 3 points total, 1 point for the position expression, one point for the trapezoidal sum, and 1 point for the position at time 12. So 1 point for your expression, 1 point for the trapezoidal sum, and 1 point for the position. And for part D, I will squeeze this on here. Okay, 2 points for implicit differentiation of, what do they say, distance relationship, the distance relationship. And then 1 point for the answer. 3 points total. Okay, so 2 points for when this was worth 2 points right here. Okay? And then 1 point for our answer. Okay, that was it. These tend to be a little bit longer problems. Data problems tend to be a little bit longer than some of the other less long problems like graphical analysis problems. But hopefully everything makes sense. Hopefully your memory was jogged a little bit on IVT, MVT, things like that. So try the rest of these problems on your own and let me know how you do.